Hello friends, welcome to Joy of Life. So today we are again going to see a hard problem from Leetcode, problem number 32. The name of the problem is longest valid parenthesis, and it's a hard problem. The problem number is 32. You can see here. The problem is pretty straightforward. So it says given a string just containing just the characters this and this. So it can have a opening bracket or a closing bracket. Find the length of the longest valid well-formed parenthesis substring. So here two things are important. So one is the well-formed. So what does well-formed means? Well-formed means every opening should have a closing. So if you can see over here that this opening does not have a closing. So the first character itself does not have a closing. It would have been well formed if there would have been a closing over here, but it's not there. So what happened in this case is the only valid well formed substring is this part. So the answer is 2 for this. So you can see over here that it's 2. Similarly for this, for the closing, we don't have a opening. So this part is malformed. And again, there is a closing, but there is no opening for it. So this also makes it malformed. So the only valid part that we can see is sitting in between over here. So the answer for this is 4. And if we are given with a blank string, of course, there is nothing, there is no opening or closing. So our answer um, to this problem is 0. So we are going to look at the solution, the approach, and the idea behind the same. But yeah, I highly recommend as well always that you can pause the video and give it a try yourself. This is a very interesting problem. You can just try to think about some solution and then continue and take a peek at my solution. So over to the solution. So what we'll do is we'll move to the whiteboard and discuss the solution there, and later do the coding part as well. So we are going to look at some of the cases. So one case could be that you have two valid options. So this is itself is valid, this is also valid, and this piece in between is the malformed one. So here we have two answers. This would contribute to 4 characters, this will contribute to 6 characters, and we need to find the longest one. So of course between the two, 6 is a clear winner, so 6 is will be the answer. Similarly, we can have completely malformed, something like this, wherein there is no valid substring over here, which is well formed. So the answer would be 0 in this case. Or we can have a perfectly valid one as well, wherein the answer would be 6. So everything is well formed. So we are going to look at the solution. Uh, how do we approach this and how do we solve this problem? So before we begin, let's take a input that we'll be working upon, and then we'll see how uh, we can apply them to these corner cases as well. So let's say I have a input string, something like this. So let's put the indexes over here. So this is a string which has 10 characters. So I have marked out the indexes, and what we are going to do is we are going to use a data structure, that is stack over here. We'll see how stack will help us to identify the valid well-formed pairs and how it will eliminate the malformed ones and keep them in the stack. So as you might be already aware that the stack is a LIFO data structure. So LIFO means the last element to go in comes out first. It's like a, a tray of plates, a crate of plates. So the last plate that you put in comes out first when you take it out. So we are going to use stack in order to solve the problem, and in the process we are also going to define the rule that we'll be using. So first let me build a stack over here. So this is my stack, which is initially empty. Now there are only two types of character that we are going to encounter over here. So one is a open bracket and the other one is a close bracket. So now we are going to lay down the rules when we encountered uh, these characters. So let's say we start iterating the string, input string from 0 and go on to its length. So whenever we see a open bracket, what we are going to do is just, so there is only one rule for it, that push it to stack. So there is nothing much, and we are just going to put the index, because since we are dealing with the length, so we are not interested in storing the character itself, wherein we are interested in knowing its index. So when we encounter this character at the 0th index, we are going to store the 0 in the stack. Okay. Now we lay down the rules for um, closing brackets. So closing bracket, when we encounter a closing bracket, the first thing that we need to check if the stack should not be empty. Okay, so before that, let me talk a little about the functions that we have in the in stack. So one is push, to push something inside the stack. The other one is to pop. Pop means removing an element out of the stack. And also we have another functionality over here, that is peek. Peek is you get to know the last element, but it does not get removed from the stack. So when we encounter a closing bracket, the first thing we should check it that the stack should not be empty. I'll tell you why it is so. And then what we are going to do, we are going to peek at the topmost index that we have in the stack. And if if the character in that index, so our first criteria is stack should not be empty. Stack not empty. So in this case, when I encounter this closing bracket, is my stack empty? No, my stack is not empty. It has element. So what I do is peek the stack. So when I do a peek, what I get? I get a 0. And now I check what is present at at the index that I got from the peek operation. So I see the index is what I get is a bracket, is an open bracket. If these conditions are satisfied, if all of these conditions are satisfied, then what we are going to do is we are going to remove this element from the stack. Why it is so? Because when we are encountering a closing bracket and the last element of the stack is a opening bracket, that means that we have found a valid pair. Okay, so in this case you can see that first when we got a opening bracket we pushed it in. When we get a close, I need to know that the stack is not empty. So why that check has been done? What if the input would have been something like this? In that case, this is not well formed, right? Because it did not have a starting. If my string is something like this over here, so the first element I encountered is a closing bracket and my stack is empty. Then I have nothing to remove, right? Because the stack is empty. Or what if my input would have been two closing brackets? So in this case, what would have happened? I have put 0 inside the stack, and when I came to 1, when I came to this index, I should ensure that I have already seen a opening bracket, and that was the last seen element of my string. So to prevent those scenarios like the corner cases, the edge cases, or the negative scenarios, we have these conditions in place. Okay. Now again at 2, what happens is I see a open. So when I see a open, I do not do anything and simply push it to the stack. And when I go to 3, the index, third index, what do? I do the same thing. Is it a close one? Yeah, it is. So this is true. Stack not empty. True. Pick the stack and see if it is a open bracket or not. All of them are true. So I'm going to remove it. Similarly, when I'm incremented towards the fourth, I just push it. When I move to 5, again I see that all my conditions are satisfied. So what I do is I move it. Okay, so when I go to 6, so what happens now is I see a closing bracket. Stack not empty. This becomes a false condition because my stack is empty. I do not have anything on my stack. Then what do I do? If these either any one of these is not satisfied, what I'm going to do is, so I'm just mark it over here. We are going to push that element into the stack. So you can see that 6 get pushed into the stack. And we increment. We reach 7 and we store 7. And then we come to 8 and all of my conditions are again satisfied. So 7 is removed. We increment to 9. So again 9 is inserted to the stack. I go to 10 and all of these conditions are again satisfied. So this is removed. So my stack has only one item, that is 6. And you can see over here from this input that 6 is the malformed characters. And we will soon see that how we will use this stack, the stack that we have built, in order to find out our result. Okay, we'll see a couple of examples. So what happens over here? Now my stack is having one element, that is 6. So just consider that if my stack would have been empty, so if I would have had a input like this, then my stack would have been empty, right? Because everything is well formed. In that case, I could have said easily that my input dot length is the biggest string that can be that we can say is a uh, well-formed input, because I have nothing. There was no malformed characters that was present because everything was parsed properly. So in that case, I would have returned the length of the input itself. But in our case, our stack has an element. So what do we do now? So we got our data that we are looking for. And now what we need to do is we have to iterate. So I'll say iterate until stack empty. So what are we going to do now? So our stack might have more results, right? So, but we have one element at the moment. So we start getting the elements out of the stack. So say we have a variable idx and we do a stack dot pop. So what we get is 6, right? So we need to find our max valid input string, right? So let's say this is our final result, which is initialized to 0. So in the index I got a 6. Now what are my possibilities? So I know that uh, I know that the right the so let's take a variable over here called right, okay, which will be at input dot length. So right currently is sitting at 10. Okay, so what I could say is right minus index. So I can say max equals to right minus index. So what happens? Right is sitting at 10, which is at the extreme boundary, and index is sitting at 6. So we get 4 from here. So we do a math.max basically of max and this equation. So what we get, max is 0 and this is 4. So our max is now set to 4. So what we basically evaluated is this part. So we got this index, we evaluated this part, right? So now what happens? Um, I set my right to index minus 1, and we iterate again. But this time I don't have element in my stack. It is empty now. We have popped only, there was only one element and we have popped it out, right? So again, outside of this iteration boundary, we do a math.max between my current max and index. Why do we do it? So we got a 6 and we have evaluated its right. Now, since I know everything is well formed before 6, so what happens is 6, I know 0 to 5 had all the right well formed data. So my max is currently sitting at 4 and my index is sitting at 6. So I get a 6 over here and I return the 6 and this becomes my result. Okay, so let's say we have let's see this iterate part when we have mode malformed data. Okay, so we have already seen that if we have a closing like this, say I have something like this, let's say. So 0, 1, 2, 3, 4, 5, 6, 7. So I know at the end what will happen is my stack will have two elements, 0 and 6, right? Because this will be pushed but will never be popped. So this part is well formed, this is well formed. So I'm sorry, this will be 5, not 6. Okay, so let me put it again. So 0 and 5. So now when so let's see how this loop will help us evaluate those cases. Okay, or let me take another, let me make it a little more complicated. So let's say I have an input like this. So I have a well-formed part here, I have a well-formed part here, I have a well-formed part over here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what will happen is my stack will have 2, which will be pushed but never popped. It will have 2, it will have 7, and it will have so yeah, so we have 2 and 7 and rest all is well formed. Or let's say we have an opening here as well which didn't have a closing. So we have 10 as well. So we have 3 elements in the stack and we'll go by this logic. So what will happen is right will be initialized to 10, the length of the string, right? And the max will be set to 0. So initially I don't have a max. Okay. And now what happens? We start the iteration. So we'll start the iteration and we'll start popping out elements from the stack. So first what we get is a 10. Okay. So the first malformed uh, data that we'll get out of the stack is a 10. So what we are going to do with that 10? So let me just put it here so that you can see. So we know that we are going to find out max, and to find out max we are going to use the max function with max along with uh, right minus index. So on the first iteration what will happen is max is set to 0 and right minus index is 10 minus 10, which is also 0. So the max will remain at 0 because there is nothing well formed after 10. Okay, and now I have to adjust my right. So I have checked this part, so I have to adjust my right. So I have to set my right over here. So now what I'll do is I'll change my right to index minus 1. So index minus 1 is 10 minus 1, which is 9. And now this loop will iterate. I have more elements, so now I get a 7 over here. Okay, my max is currently sitting at 0 and I know my right is sitting at 9 and I got a 7 from here. So 9 minus 7 is 2 and I get a 2. So my max is set at 2 now. Okay, and you can see that in this input after 7 the valid part is only 2 characters. Okay, so again I adjust my index. Now it becomes, so where is my index? So my index is at 7. So 7 minus 1 I move it to 6. So again, so these two elements have been popped, right? Now I pop again, I get a 2. So my max is currently at 2 and my right is sitting at 6. So 6 minus the index we got is 2. So I get a 4 over here. 6 minus 2 is 4. So my max, previous max was 2. So this max will be set to 4. And you can see here that it is indeed 4 characters long. Okay, and I'll adjust my right. Right will come to index index minus 1. But we have consumed this 2. So there is nothing more in the stack. And remember how we did this max part out of the loop? Why? Because we want to consider this left side as well. So we have to look at the left side of the first malformed character. So what we did in this case was out of the loop. So this is out of the loop. I'm just keeping a dotted line over here. So we are just considering the max again, and we are taking a max of current max versus the index. So current max is set to 4 and the index is set to, the last index I got was a 2. So the answer remains at 4. So you can see that these two, this two, actually represent this. So we have considered all the possible well-formed substring of this entire input. I hope you got the concept right. And also just wanted to give you an idea if some one of you might have a doubt regarding it. So this is a well-formed input, right? So if this is my input and these are my indexes, so what will happen is I'll push 0. So I said that whenever we see a open, we just blindly push it. We get a 1, we push it. We get a 2, we push it. So when I get a 3, we fall back to check all these three conditions. All these three conditions over here. So you can see that all this condition is satisfied when we are at the third index. We remove it. We at 4, all the conditions are satisfied. We remove it. When we are at 5, all the conditions are satisfied. We remove it. So there is nothing in the stack. So my result become input string dot length. So our result would be 6. So in case of a malformed string also, you'll see that both the index will lie on the stack and it will be never removed. So I hope you got the idea how we are leveraging the stack in order to come to a solution. And I hope this has given you a pretty fair idea of how to deal with this problem. And now we are going to quickly look at how we do it in the code. So first we'll check that if the length of this input is 0 or this input is null. So if these two cases are there, then we can return 0. Okay, and because we did not get an input or the length of the input is 0. Now we are going to look at our solution. So as I said earlier that we are going to use a stack, and let's say the name of it is also stack, and we are creating a stack of integers. So because we are going to store the indexes, not the characters. So that's why we are using a integer over here. And what we are going to do is we are going to iterate this entire string, right? So what we can do is length and do a I plus plus. So let's say we get this character. So the character is, we can get it using caret function, caret I. So now as I told you, right? So first lay down our second part of the code, which is this part. So we have already laid down the rule over here. So there are three conditions to it over here. And we are going to put it one by one. So the first condition has to that if ch is equals to a closing bracket, If ch is equals to a closing bracket, then we have two cases. The first one is to pop out. When do we pop out? So basically we have to ensure two things in order to pop out. That the stack should not be empty. So stack is empty and I have used a not operator in the front. And the other thing that we are doing was a peek, right? So that will give me the last element, the index of the last element in this stack. So we are going to check s.char at the peak position. It should be a open bracket. I think I messed up some few things over here. Yeah. So it has to be either of the two, both of the two. And then if both the conditions are satisfied, in that case, what we can do, we are going to pop out of the pop the element out of the stack. But if not, if it is not, then what we are going to do, we are going to add that element to the stack, right? So that's what we did over here, that if any of these conditions fail, if any of these two conditions fail, we are pushing it to the stack when it is a closing bracket. Else, there could be only one possibility in else, that is we get a opening bracket. In any ways, whatever it is, we are going to push it. So in Java it's called add, not a push. So let me change it here. So we are done with the addition part. So this addition logic that we are building the stack is done now. So now one happy part that we have talked about, if your stack is empty. So if there is no element in my stack, that means there is nothing malformed over here. So what I can do in that case is I can simply return the length of the input string. Everything is well formed. Or what we are going to do is we are going to use this max variable in order to capture our final result, and we need the write. And as we discussed earlier, the write will be at s dot length. Since it's zero based index, so we are going to do a -1. And we need a temporary variable idx. That's what we named it over there also. And we don't need to initialize it. And we are going to iterate until the stack is not empty. And in the idx, what we are going to do is we are going to extract, we are going to pop elements out of the stack. So we are going to do a stack.pop. And once we pop the element out, we are going to figure out what our max is. So we are going to do a math.max in order to compare with our current max. So current max is set to 0, and we are going to check with write minus idx, right? That's what we have done over here, right? So we are going to do a write minus idx. So we are done with this part, and then we have to adjust our write pointer. So what we are going to do is, right, we are going to set it to idx -1. So we are adjusting the index. So we are done with all the elements inside the stack, and now we have to consider the left part of the first malformed character. So we are going to do a math.max of the current max along with the index that we have. And once we are done, or we can just say, we can just return it from here. No need to assign. Oops, I have the insert pressed. So yeah, this sums up the entire algorithm. So let's run this and see how it goes. Okay, this should be stack, not S. I have plenty of silly mistakes I think I have done over here. Okay, I haven't initialized it. I need to initialize it because we are using outside as well, right? It could happen that it doesn't go inside the loop at all, so we need to initialize it over here. So it was successful with our test input. We can run with the input that we tested for. So this is our happy path, one input. So you can see the length is 10, and let's make it unhappy with a malformed character in between. So ideally it should be 6 because we have 6 valid characters at the right, this part. So I think we're getting the expected result. So let's submit and see how it goes for a broader range of test cases. So yeah, you can see that it has been submitted. It's taking 3 milliseconds, which is pretty fast. And of course, there are places where you can optimize. I'll leave that to you. But I think you got the overall approach of how to solve this problem and how to come up with the answer. So I hope you like the video. To share your thoughts, to share, subscribe, do encourage me to create more videos. Thank you once again. Have a great day. Bye bye.